thanks a lot, and thanks for inviting me, and thanks for organizing this nice meeting, and glad to be back in Tel Aviv. This will be about some variant of billiards, but will also be about celestial mechanics. And the basic idea is that you should consider limits and see what these limits can tell you. So, I mean, if you teach linear algebra or analysis, then sometimes you have the problem of motivating people. Yeah, so they say, yeah, why do I need this? And so, and then you say, oh, you will say later everything you learn in these courses you will need in higher semesters and so on. But okay, then they have to rely on my experience. So this is doesn't work very well, especially prospective teachers. Students say, oh, I definitely know that I don't need this in school. Yeah, so why should I learn it? And then maybe it's better to have an intrinsic answer. And for linear algebra, this is quite simple. You just say, look, it's like a crystal. Everything fits together, and it's just a beautiful structure, which is in some way simple and at the same time quite complex. For analysis, you have inequalities instead of equalities, so it depends much more on choices, and it's more like a jungle than a crystal. Answer is harder, but one answer you can always give, and I think this is an honest answer, is that the basis of analysis is limits. Yeah, and limits is something very powerful. For example, limits of rational numbers can give you irrational numbers, so it's something new. Yeah, or limits of polynomials can give you analytic functions. This is something new, and this is really the power of these limits that one should always look at. Yeah, so after this introduction, that's also the main idea here. So more specifically, look at temporal limits. Yeah? So time limits in scattering dynamical systems, like, for example, you have in celestial mechanics. Yeah? And look what these limits can tell you. Yeah? And so you could look at time limits for singularities. You could look at time limits for whatever is asymptotic velocity. And that's what we will do. Yeah? So the setting is, of course, one of a Hamiltonian system with phase space R and D, because you have n particles in d dimensions, and then it's of the typical classical form, kinetic plus potential. And more specific, just for the sake of simplicity of the talk, I will assume that two particles just will interact via a homogeneous inverse power of their distance. Yeah, and because of that, you don't want to have two particles in the same place, because of reasons that you're probably well aware of. You better take homogeneous powers alpha between 0 and 2. Okay, and because you don't necessarily think of celestial mechanics and its variants, this could be non-negative, these interaction strengths. Let's think of electrostatics. Yeah, one could, in many of the things that I say, be more general than that, but I don't want to do. Yeah. So the first question I want to pose is a very simple-minded question. So can we say that solutions of the Hamiltonian equations exist for all times? Of course, we know that in celestial mechanics, you can't expect this because there are collisions already for two particles. So can we say that for almost all initial conditions, this is possible? Yeah. So that's the first question. Yeah. So just, yeah. Up to I just defined this. Yeah. Okay. So that's just a general question in a dynamical system. So you have a vector field on a manifold P, and you just look at the ODE connected with this vector field, and then you get a maximal flow phi, and this maximal flow phi has initial conditions x on the manifold, and you have some time t, and the time for a given x is between escape times t minus and t plus, and you cannot extend this anymore. So that's the maximal flow. Yeah, and of course D is then an open subset of R cross P. Yeah, so that's a completely general concept, and the singular set is then just defined to be those set of initial conditions, the set of initial conditions where this T plus is finite. You could of course also think of T minus, but especially because these systems I would consider are reversible, just stick to T plus and call it T. Yeah? So, okay, so that's a general ODE definition of singular set. And if you have the situation of scattering theory or these Hamiltonians, then you can be more specific. You could also call about collision singularities. So what is this? This is just a set of singular initial conditions where the limit of positions exists for this escape time t. Yeah? And then if this exists necessarily, it must be in this fat diagonal. Yeah. So that's the collision set of collision singularities. And of course, then you have to complement whatever this is. These are the non-collision singularities. Yeah. So the idea is now to look about the geometry connected with it. Yes, exists in RND. Yeah. Yeah, there's no one-point compactification or whatever at this point. Yes. Now, here, of course, this. If you think of the singular set in general terms, then the limit doesn't have typically some interesting structure. For example, you just are on R2, and you have the vector field is just a unit vector field to the right, and then you take away one point of R2, and then if you start from the left of this point, then you have a finite time, but otherwise there's nothing interesting in this limit. But in celestial mechanics, things are different, and this is just shown in these two pictures, basically. So let's first think of collision singularities. As we know, the particles that experience a total collision asymptotically go to relative equilibria, at least after rescaling. So there is some important structure in these collision singularities that you wouldn't see from the outset. Yeah? So that's one geometrical structure of this limit that is important. And concerning non-collision singularities, so they were anticipated in Parlevé in his Stockholm lectures in 1897, and took quite some time until Jeff Shea proved existence in 1992. Yeah, and that's what his construction works looks like. You probably know it. You have 5 particles in R3. 2 pairs are all the time in horizontal planes, and roughly speaking, they move on ellipses around their common center of mass, and the center of mass is on the vertical line, and there's a 5th particle going forward and backward and pushes these two binaries in finite time to infinity. Yeah? So that's an example of the non-collision singularity. Yeah? And sure. Sure. I mean, n-particle interacting systems in classical mechanics always are in cannot exist in relativistic theory. It cannot even interaction of just a finite number of particles within relativistic theory doesn't exist. Yeah. Okay.
The particle statement is opposed to this
yeah.
They collide. So there is both.
Yes. Yes, and this is very important because the total energy is conserved. That's the reservoir where this kinetic energy of the particles comes from. Yeah, so that's the most important point. Yeah. 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 It can be everything. Yeah. I mean, there are variants of this that are quite free to do whatever you want. Yeah? It depends on how small the distance between these particles was at the beginning. Yeah? Okay, so there was another quantity I want to talk about, not only singularities, but also this asymptotic velocity. So what is this? You can just define this rather generally. So if you, for some initial condition x naught, have position in some RK for some dynamical system, maybe mechanical, and if you then look for the Cesaro limit of the velocity, so of q prime, then this is this quantity, the mean integral in the limit of time going to infinity. And you can, of course, write this like this if you want. So that's asymptotic velocity. So the question, and this was a basic question in quantum mechanics, varied quantum mechanics, and also in classical mechanics, do in these scattering systems these quantities exist for, let's say, almost all initial conditions. And in fact, it was first proven in quantum mechanics and then in classical mechanics that they exist under some assumption, namely, if you instead of these homogeneous pair potentials, you have some bounded C2 pair potentials, Vij, then asymptotic velocities exist for all initial conditions. Yeah? And this is called asymptotic completeness, and the proof is not easy. This was in a paper by Jan Deresinski, and is well documented in the book with Christian Gerard. Okay, so of course, if you have a non-empty collision set, then for the points in the collision set, you cannot even define this because then time doesn't go to infinity. But otherwise, there could be other reasons why this doesn't exist. Yeah? And so the next question is, of course, does for these variants of the celestial mechanics and body problem, does asymptotic velocity exist for almost all initial conditions? So these are different but difficult questions. So what does one know? So in papers from the 70s, Banzari showed that in all relevant dimensions of configuration space, so starting with d equal 2, and homogeneous interactions of the form in celestial mechanics, the collision set is of zero Lebesgue measure in phase space, and alpha was then between 0 and 10/7. Yeah, so not exactly going to 2, so that settled more, at least for celestial mechanics the problem, because then alpha is equal to 1. Yeah? So for n equals 1, 2, or 3 number of particles, non-collision singularities cannot exist, yeah, because the particles separated in some way, or at least some particles separate from the other two, whatever. Yeah, so the first non-trivial case is 4 particles, and then Bernard also showed that this non-collision singularity is of 0 Lebesgue measure for the relevant case of celestial mechanics, and probably one can generalize parts of the results, but not quite, because he also uses this special form of the Keplerian singularity, which leads to backscattering. So whatever. So we had then found some new methods to prove things, and so our statement with Stefan Fleischer is that if you fix any energy for this total energy of the system and any alpha between 0 and 2, then inside the energy surface, the set of collision initial conditions has Liouville measure 0, and concerning the non-collision singularities, you have the same situation, at least starting from p equal 3. And also in this case, this asymptotic velocity exists almost everywhere in your energy surface. Yeah. So, but still, there's a large gap between n equal 4 and n equal 5, and this is completely open, and this is a complicated question. Yeah. So, question: can one use this mantra that limits are important to understand more about the limiting dynamics of these non-collision singularities? Yeah, so look at this picture. So you see here, I mean, everything going to the right so that you can see something in the picture. But basically, what you see is that these everything, then goes asymptotically near the singularity, near T plus, on straight lines. Yeah, so that's basically the picture. So it's a kind of billiard. Yeah, so it's a kind of billiard that these particles play. And the question is whether one can learn something from this analogy with billiards. Of course, everybody who thinks about these problems will compare these motions with lines or segments of lines. Question is there some relevant dynamics, billiard dynamics, that is should be considered? Okay, so in fact, one can also ask this question in situations where you don't have any singularities. So first, look at this left-hand picture. So you have here in configuration space some trajectories of particles with different color codes, and these particles are billiards, and then they meet these particles at some points and change their direction and so on. And so the question is whether we can imitate this in, for example, celestial mechanics. Yeah, so what one would like is to start with the left-hand picture and then go to the right-hand picture and actually find solutions in celestial mechanics that look like that. Yeah, so that's a basic question where you can play billiards here. But of course, these kinds of billiards are somewhat unusual because these are point interactions. They just have to meet the 2 points. Yeah, so never mind. And there's another problem here concealed in the picture. Here you have a 3-body interaction. Question is what this really means here on this side. Yeah? So now how could we model this? So first of all, we want to model the left-hand side, of course. So between collisions, these billiards move like billiards move and with constant velocity. At collisions, the energy, total energy, should be conserved. Total energy of 1 and 2. You see here the numbers of the particles colliding, and also the total momentum of this cluster composed of 1 and 2 should be preserved. Yeah? Then what we want to do is to make such a picture, but to abstract it a bit, just to prescribe a temporal timetable, so to say, of these collisions, and then look at all the realizations of such a billiard which obey this timetable. Yeah. Yeah. So this is then a non-deterministic dynamics, because here at such a collision, the particles have to preserve energy and have to preserve total momentum, but otherwise they are free to change their internal direction. Yeah. Okay. So you can. I mean, I define this in a moment. Yeah. So probably it's. I mean, I would just say that every such picture is fine if these rules are obeyed. Yeah? Then this is a realization of this non-deterministic billiard. Yeah. Okay, so let's do it a bit more formal. Abstract this a bit further. So you choose a finite set of linear subspaces, L of an Euclidean subspace of capital dimension D, ED. And in the discussion above, we had n particles in R small d. So phase space should be R and D, or abstractly E to the D. And then we, as a choice of the subspaces, we would concretely have the choice being by indexed by two-element subsets of the index set 1 to n, and Lij is just the set of points Q where Qi equals Qj. Yeah? So these are subspaces, and we have scattering by these subspaces. And the next item would be to define this non-deterministic billiard, as I indicated. Scattering with respect to this family of subspaces, preserving energy and tangential momentum tangential to this subspace. Yeah? So that's everything that is a solution of this problem is fine with me. Yeah? Then you could choose an itinerary, which means choose a succession of subspaces and look for the possible realizations of collisions with these subspaces in succession, and then you get a set of trajectories called this B, depending, of course, on the choice of succession of subspaces, meeting these subspaces in the order. And theorem, together with Jacques Bejosse and Richard Montgomery, says, first of all, by basically a statement by Burago, Verleger, and Kononenko, there's a finite number such that capital K, if this small k is larger than capital K, then this set is empty. There's no realization. Yeah? Second point, there are more points, but I focus only in this one. There's a Lagrangian relation defined by this choice. So what is a Lagrangian relation? Generally speaking, you have a submanifold in a product manifold of symplectic manifolds. Yeah, that's a Lagrangian relation, and that's also what we get here. More specifically, our symplectic manifolds are the cotangent bundles of d minus one-dimensional spheres. So these describe incoming and outgoing oriented lines before and after this succession of collisions with the typical symplectic form on this product space. Yeah, so that's like if you would have a deterministic system where you would have a map from the first data to the second data. Yeah, but only like that. It's not a graph. Yeah, this relation is not a graph. Yeah, so that's structured. Yeah, if you could. Yeah, that's a good thing to compare with. Yeah. So, what does such a realization look like? I mean, here you have just an R3, 3 one-dimensional subspaces, and then you see this orange trajectory. So it goes from L1 to L2 to L3, and has initial and final lines as directions, directed lines, incoming and outgoing lines, and basically a set of all realizations of this is a Lagrangian relation. Yeah. So because of this basically Porago-Feliger-Kononenko theorem, the dynamics is integral because after some time everything calms down. Yeah? So nothing more happens than free motion after this time. Yeah? So even in spatial dimension, where the situation is of course a priori a bit different, because there if you basically I mean need to collide if you are not in a very special situation. Yeah, so even in low dimensions, this is true. Okay, there is a lot of related results, but only partially related. Therefore, I don't talk about too much by Sergei Volotin in this proceedings. Steklov Institute article on the general billiards. I recommend it to you. So now. I don't want to be deterministic, but I don't want to preserve energy either. Yeah. So I'm stripping away everything I had from the structure I had in the beginning, namely the deterministic billiard. Yeah. And this for good reasons, because if I think of this Shia example of these two binaries pushed to infinity by this messenger particle or star, then you see that the kinetic energy is not preserved, but increases without any borders, so any limitations. Yeah. So if you want to model this by a billiard, then better you don't keep the energy fixed. Yeah. Because then kinetic energy is just the total energy. Yeah. For this billiard. Okay. So now I tell you my first approach to this, so unfortunately this talk is also a bit about modeling and maybe ways to model better, but I think this is necessary in this context to also go the wrong ways, or not completely wrong ways. Huh? So in the beginning I had the idea just to model for example this Shia example by 3 particles. Yeah, because you have the messenger particle and 2 tight clusters, and from far away you don't see the tight clusters. Yeah, so and then clusters can then you have n clusters, let's say, and of course also these cluster centers of cluster centers can collide. You should have in time a continuous curve in your phase space, in your configuration space RD, and you should have constant velocity q prime until you exactly 2 of these clusters collide. And of course, for this Shia example, this is completely satisfactory to understand this, or to assume that exactly 2 of them collide. And then you have these momenta of this the ice cluster, and the external momentum before and after the case collision should be the same. So this I don't want to give up, but so the center of mass of these two clusters moves with constant velocity until one of the clusters collides with another one. But this internal momentum, this may change arbitrarily in direction, but also in energy. Yeah? Okay, so now also some wish to make mathematics simpler, and also something that is satisfied in this shear example is that the number of collisions in the future is infinite. Yeah? Quasi-collisions for the deterministic problem, collisions for this billiard model, and they occur at times that can be ordered in ascending order, yeah, and just accumulation point at t plus. So, and this suffice, so that would be a typical realization. You have, for example, here 3 particles, or 3 clusters with their positions in the plane, configuration plane. So, for example, here, the second and the first particle collide, and then the second and the third particle collide, and then again the second and the first particle collide, and so on and so forth. Yeah. So what can one prove about this? Just for this n equals 3 non-deterministic clusters, yeah, or however you will call. So one quantity that is of interest is that is this J for arbitrary number n of particles. That's just this quadratic form in position with multiplied with the masses. And so now the TK here are that come in the next point are just the times of collision of any such realization of this non-deterministic system. And the statement is that if initially you go outside in the sense that G prime is positive, that this not only stays like that, but even T of Tk grows at least exponentially with K. Yeah. So without any assumption on energies, or so you have this lower bound. Yeah? And then you can prove the same kind of estimate for the kinetic energy. This also grows exponentially, even a bit faster than this J. And the angular momentum, still in this case, of every such cluster with the number I, for 3 clusters, this remains bounded. Yeah? Not only the total angular momentum, but the angular momentum of every particle. And this means that asymptotically, these 3 non-deterministic particles are on the line as t goes to this escape type, yeah, on a fixed line in configuration space. So that's what you get just from considering these 3 particles. And that was an input to analyze the 4-particle deterministic system with homogeneous potentials. And then the statements could be proven that for arbitrary alpha between 0 and 2, this non-collision singularities are of measure 0, and also the set of initial conditions where the asymptotic velocity doesn't exist is also of measure 0. Yeah. So basically here in this case, the 3 non-deterministic clusters can model the motion of 4 deterministic particles, for example, celestial bodies, because you need 1 tight cluster, yeah, because that's the energy reservoir for kinetic energy. Yeah, so that's the minimal number, so to say. Yeah, so unfortunately, none of these statements above is true if you have more than 4 clusters, or here more than at least 5 non-deterministic particles. Yeah, everything fails. Yeah, and that's maybe something important to know, because since the 1970s there has been not much progress in this question of these measure zero of the collision set, the non-collision singularity set, and I guess part of this problem is connected with this failure of all these statements for this asymptotic non-deterministic billiard motion. Okay, so what to do? Unfortunately, there will be another modeling, and I hope that you still survive this. This is more combinatorial. Anyhow, the end is near. It's 8 minutes. Huh? That's what I say. Yeah. Okay. So the end is near. Not of the world, hopefully, but the talk. So you have n particles. Yeah. So combinatorially, you consider the set capital N of these n first integers, and then you look at set partitions, or how it is called in scattering theory, clustered decompositions, of this set capital N in parts C1 up to Ck, which are non-empty subsets of N, mutually disjoint, and the whole of this gives you N. Yeah? And then take all these cluster decompositions or set partitions together, then you get obtain a lattice. This partition lattice, P of N, that's a useful combinatorial object. So this is semi-ordered by refinement. You could have finer clusters by breaking up clusters, basically. That's the idea. Or more formally saying, you could say, okay, you have 2 such set partitions, and the first, namely C, is finer than D. If one can map the mth atom of this first into the P of mth atom of the second set partition for some such map. And that's something that has been studied, of course, in combinatorics. Not very complicated thing. You have the rank, for example, the number of these atoms. This would be K in this case. And given 2 such cluster decompositions, you can look at its meet and its join and so on and so forth. Okay, so that's now the language I want to speak. Just for an example, for 3 particles, you have exactly P of N consists of 5 such set partitions, and here you see them with a slightly different notation and with their ordering, and the vertical is the rank. Yeah? So now, if you have such a set partition, C, then you can associate with this the subspace, which I call delta C, in configuration space, where the i's and the j's particle have the same position if they are in the same atom. Yeah, the indices are in the same atom with respect to C. So you would see here also 5 such subspaces, because you have 5 such set partitions. So this is in the center of mass configuration space. You have 3 particles in configuration space R. So dimension is 1. So this means you're on R3, but you're in center of mass, so you're in R2. So one of these subspaces would be R2, and then you have the red, green, and blue subspace corresponding to this rank 2, and then you have this subspace here, which is rank 1. Yeah. So then you can also, and that's useful, decompose these subspaces if you change this if into an if and only if. Yeah. So then you have a decomposition of, in this case, R2 into these xi C subsets. Yeah. So and if you have a point Q in configuration space, then you can project it to the subspace delta C and call this QCE. So basically, you just record the centers of masses of these clusters. And for example, for the red one, you go to just down here. Yeah. And E is just for external. You could do a similar projection for internal motion within the cluster. So that's a language that is typical. Now I can define this non-deterministic system as I like this. Now particles are modeled, yeah, not clusters. So particles have masses, and so certain continuous curves in configuration space are called non-deterministic systems with these n particles. So these are defined on some interval. The boundaries of the interval are the escape times, could be infinite or not. So now the first thing is that if you have such a curve arbitrarily chosen, then you get a subset of your time interval I, call this T, where this CS function is not locally constant at this T. So what is CS? Given a point Q of given a time T and a point Q of T, this is in exactly one of these parts of the partition, set partition of your configuration space. So you get for every T such a set partition. And if this set partition is locally constant, then you're not in this T. If it's not locally constant, then you're in this T. Yeah. So what do you want? So first of all, if you're not in with your time in this singular time set, then the velocity of the system is constant as before. And for all times, the map, which only looks at the motion of the centers of mass, is continuously differentiable and locally just again constant, so external momentum being locally constant. And last condition, if these escape times are not plus minus infinity, then there must be reasons, and the reason is then that there's a limit that this limit Q of T doesn't exist.
How the mass center
through the momenta, because the momenta I somewhat, I guess at this transparency didn't write them, but the momentum of the ice particle is mi times qi. So it's basically the Euclidean structure that you change. Yeah? Okay, so this definition seems more abstract, or it's more abstract, but it's in some aspects easier, especially if you would project in configuration space of one particle to a subspace. And if you have such a deterministic system of n particles in RD, and if you project this, then you get a non-deterministic system of particles in the subspace. It's kind of a compactification of the former definition. And so there's another thing, namely, instead of collisions, so-called chain closing collisions are now important. So basically, I don't have time, every indirectly has to have interacted with all other particles. Yeah, that's a next time step. And I come to the final statement. So this is with Manuel Paschner, who just finishing his PhD with me. And this J for every such deterministic, non-deterministic realization is a convex function, is continuously differentiable, P is countable and nowhere dense. If the initially grosso modo this system is expanding, then again J and K kinetic energy grow exponentially not in the number of collisions, but these chain closing collisions. There's an analog of the above result on Lagrangian relations. And finally, at escape time, each deterministic trajectory, let's say celestial mechanics, with some initial conditions in non-collision singularity, is shadowed by such a non-deterministic trajectory. The last point, there's something still to check, but I'm quite confident this is just in the last week, so that we can really show this in full generality. Okay, there are some remarks, but there's one, I'm out of time. So there's one basic remark. So this is part of, as I said, the PhD thesis of Manuel Quaschner. No, not quite that, but at least other results extending this non-collision singularities partly to more than 4 particles. This is part of this PhD thesis. And I must say that Manuel is a bright student. So if you have a postdoc position for him, I strongly advise you to take him. I would also like him to stay, but this wouldn't be a good choice. And therefore, that's what I want to say in the end. Okay, thanks. You're welcome. Mm-hmm.
Did you ever mention when you were speaking about the measure of collision sets and so on? You didn't mention the total angular momentum.
Yeah.
I remember from some previous articles that this quantity is absolutely crucial when determining whether the measure of the collision.
Yeah. Yes. So if alpha is, I always excluded alpha equal 2, and for alpha equal to 2, you just can have a one particle system in a force field with inverse second power, and then you see that with a certain non-zero angular momentum, you still collide in finite time, and that of course cannot appear for celestial mechanics and for all other alpha. So that's really what is basic to all these measure zero results. Huh? I guess that, yeah, there have been comments on this. But actually, I forgot the statement. I'm sorry. Of course, what should be said is that nowadays there's also an example of such a non-singularity for 4 particles in celestial mechanics, but this is just the usual 1/, distance. I forgot. I'm old. Sorry.
Well, there's a question, but one thought for relativistic effects.
Mm-hmm.
Would one model by classical, but by choosing alpha?
Mm-hmm. Yeah. 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 Before I stated this no-go theorem, you've no n-particle classical physics or even quantum physics which is relativistic. Huh? It doesn't exist. Huh? It's not compatible. You need infinitely many particles. Huh? But and I think this is quite an interesting statement. But you could, in a perturbative way, of course, just define this Hamiltonian. And what would happen then is that I mean, you have this square root of m's mass square plus momentum square expression. No, what is it? At least, yeah. I mean, basically, what you get is that asymptotically, the kinetic energy becomes linear with momentum, yeah, with the norm of the momentum, and this means that you basically can get black holes by this quite naive consideration just much earlier for smaller alpha than before. Yeah?
What I had in mind was the helium recession, because if you look at this effect, similar recession would happen down from one to something. I'm not sure we've got something positive or not.
Yeah, this I don't know, but yeah, but I think what this could be worked on. But I mean, a proper scattering theory would work because then particles would have a positive probability. Have some structure, the Lagrange relation structure imitates the Lagrange. Every symplectic map can be considered as a Lagrange graph, yeah? And so these Lagrange relations somewhat imitate Lagrange graphs, and so here to then on course. So that's how to come.